So how many labs are there down here, Helen?
We've got about 3 or 4 labs that do astrochemistry.
Okay, and this is Astrochemistry 2.
Astrochemistry 2.
Can we go in?
Yeah, come and have a look.
So what kind of research happens in here?
Right, so what we're doing in here is we're studying the basic steps that happen in planet formation. Right. What we're interested in understanding is how things stick together. It's quite a common problem. Probably you, like many other people, have been to the beach before. And you know that if you want to build a sandcastle, you learn pretty quickly not to gather the sand far away in the sand dunes, but to go and gather the sand that's near the shore of the sea where it's getting all wet, because essentially that wet sand sticks together. Now in space we don't have wet sand. All our sand is very dry. It's very cold, about minus 263 degrees centigrade. So that's much colder than even on a very cold day in the United Kingdom. So what we think happens is we think that these particles, these grains of dust that start the building blocks of planets, basically get icy coatings on them. Right. And everybody assumes in all the models we have of how planets form that if things are icy, they stick together and they grow bigger and bigger and bigger. So we built this rather large machine simply to test that. And we don't test it for all different sizes of particles, because there's also an extra thing. We know that very, very small particles will stick together. Yeah. And by very small, I mean up to about the width of a human hair or so. They can stick together quite easily. And we know very big things like kilometre sizes stick together and form planets. And we know planets exist. We've found over 2,000 of them now. But somewhere in between, from about the width of a human hair to kilometre size, actually we have no idea exactly how things stick together. So what we do with this instrument is we make little balls of ice.
Right.
And we put them inside here.
In this chamber?
Well, underneath this chamber we have what we call a Colosseum. And the Colosseum is like a double helix of holes going round. So it's engineered quite cleverly. So we fill them all up and then we turn it from the bottom of this machine.
Right.
And then just here in the middle, I'm going to move them by hand at the moment, we have these pistons. And these pistons push the particles out of the Colosseum towards each other. And then they collide together and we watch it with a very fast camera. So this camera is taking many hundreds of pictures every second, and it has a very high resolution. And when we go back to the lab, we analyse very carefully how these particles collide together. Unfortunately, what we find is that all these icy particles we've tested so far, they don't stick at all, they bounce.
Right.
But we do find something pretty interesting. We do find that they change, they convert energy. They change the translational energy, the energy moving towards each other, into rotational energy, energy rotating, which means that the particles start slowing down and rotating. So probably what happens when we really have planet formation happening is collisions start banging things together and colliding things, and we end up with, if you like, a traffic jam of particles. And if this traffic jam of particles gets dense enough, then different processes can start happening and we can have a sort of spontaneous gravitational collapse of these small particles that can then start building bigger and bigger things. And so that's one of the things we're really trying to understand with this very large piece of equipment, testing those very small things.
So planetary formation, it's all about small particles and big particles, but not the particles in the size range in between.
Well, we know that small particles stick and we know that the big particles stick. But we know we must have some sort of size particles in between, because in order to make big things, we have to have small things. So actually, our big problem is, first of all, we can't really see with our telescopes those in-between things. They have funny sizes, so it's difficult to observe them. And secondly, we actually don't know what physics is controlling those processes. So that's why it becomes really fascinating to study them.
Right. You said there was another bit of kit.
Yes, let's go over here. So here actually I have 2 pieces of kit. First of all, I have the rather complex motors that really drive the pistons. When we were just looking before, I was just moving them by hand.
Yeah.
Okay. So actually, these are also carefully engineered. We have a lot of fun. It seems very simple when we're talking about throwing 2 particles together and letting them stick. Actually, there's one other thing that we have to really consider, and that's how fast these particles are moving. And they're moving around a few centimetres per second. Now that's pretty hard to put in context, but if you imagine driving your car at 30 miles an hour, you're moving somewhere between 1,000 and 1,500 centimetres per second.
Right.
So that's quite a lot of centimetres per second when you're driving your car. And if you could slow your car down so that it's hardly moving at all, a centimetre per second moving forwards, that's tiny. That's slower than you can even move on the M25, I think. Then that's the velocity that these particles have when we're colliding them together.
So really nothing at all?
Really nothing at all. So actually, we often, although we do experiments with this in the lab, we also take this into what we call parabolic flight, which is the aeroplane, some people call it the vomit comet.
The vomit comet.
Yes.
You've been on it?
Oh yes, I've done about 500 parabolas, yeah.
Goodness
Yeah,
me.
yeah.
So what happens when you're in parabolic flight then?
Then you end up, it's like switching gravity off. You're not really doing that. What you're doing is balancing all the forces, but essentially you experience a weightless environment. So you actually go kind of floating around. Actually, we can't float around when we're doing the experiment. We strap ourselves down because we need to concentrate on doing the experiment. And because it's so, we're in a really strange environment, and because it's such an unusual environment, we're concentrating a lot. We have to do very little task loading with our experiments. We have to have very simple things to do. Press a button. So instead of moving these pistons by hand, we move them with a motor.
Right.
And the motors are all controlled, computer controlled. It uses something called an EPOS system, which some people may have heard of before, which means the motor is entirely controlled. And we have a drive so that it's a sort of gearing system, so the motor is moving in directly. And if you look carefully here, there are two electronic switches, here and here. This is the one that stops it at just the right position at the back, so we can turn a Colosseum round to do the next particle collision. And this is the one that stops it at the front, so the pistons don't bang into each other, but the particles can really move. So while we're designing and developing these experiments with our science questions in mind, we also end up engineering quite a lot of things. And here's one I made earlier.
Yeah, this is the Colosseum, isn't it?
Now, it has two pieces to it. This one's a little bit messy because last time we took the experiment into flight not long ago, we actually were using a number of chemicals. So unfortunately, they've had a bit of reaction with the system, but it's okay. They weren't dangerous chemicals, just formic acid and methanol, because in fact, some people postulated that these can make a difference to how the ice sticks together. We didn't find that either.
Okay.
But it's always good to test these things, because if they're in models and we keep making our models to make planets a certain way and that's not the way it's happening, we'll never really understand the real processes occurring. So sometimes when you do research, a no answer is as important as a yes answer. Yes. So here now, maybe you can see, if you look very carefully, if you start at the top here and I turn this round, you can see that gradually, if I follow that top layer around, can you see that it's gradually, just now I've got to the beginning again, coming under the first layer, yeah? And then if we were very clever and we look for the black mark on the other side, or the lines on the other side, we would find that there's always two holes opposite each other. Maybe I can look through and see you, yes? I don't know if I can, yes, I can do that.
Got you.
And so it's been very carefully planned with some CAD design that the double helix goes in opposite directions, so that every time we turn this, we're able to collide particles from different directions. And then actually, because we want to keep it all cold, what we do is flow liquid nitrogen through the system to keep it all very cold. But in the aeroplane, when we go in the parabolic flight, we're not allowed to take cryogens with us. Because you can imagine, in zero gravity, they're no longer contained. They no longer sit in a container nicely or anything else.
You don't want them floating off into the cabin, do you?
Definitely not, because at some point in a parabolic flight, you have a 2G phase. You have a hypergravity phase, and you really don't want anything splashing around either. So what we do is we cool everything down, and our experiment, actually, it's worth a lot of money. It has a 70 kilogram block of copper in it. So it appreciates and depreciates according to the world metal markets, actually. And
also why the lab is well locked up.
Well, and also to keep things very clean for when we go on parabolic flight, that people don't accidentally take something and we're in the middle of flight when we need it. So what we actually do is we also cover up our holes. You sort of saw this in the other system. You couldn't see the Colosseum. It hides away. And then we have guide tubes. So when the guide tubes line up with a hole, like so.
In there.
Then the pistons would push a little particle out, and we have a collision volume in the middle that we can look at.
Yeah.
So that everything is contained, and so the particles can't roll out when we don't want them to. And actually this bit stays fixed in flight, and what we actually do is we manage to turn underneath on a gear by hand, that one, because it's very heavy. That's one of the jobs we do by hand.
So your research, is it all about understanding how planets form?
My research even goes a bit further than that. So my thing, if I was sitting in the pub having a pint with you, is I would say my thing is ice. So I'm really interested in ice, and I'm interested in ice. What do we mean by ice in astronomy? By ice in astronomy, we mean any material, molecular material, that basically forms a solid at these low temperatures we have, minus 263 degrees centigrade. And we are interested in planet formation because ice is clearly playing a key role there. But in actual fact, it's also a bit of a cheat, what I've told you so far, because the kind of ice we've studied so far in these systems is what we call crystalline ice. So it's the kind of ice you could get out of your freezer, pretty much, or put in your whiskey or your gin or your Pimm's and lemonade if the sun comes out. And in actual fact, the kind of ice we have in space is called amorphous ice. And what we mean by that is it's really a very porous structure with no real long-range structure. And I used to say to people, think of it like a bath sponge. So if you think of it like a bath sponge, I don't know, when I was little, I always got into trouble from my mum for sticking my finger in one of the holes in the bath sponge and trying to make it a bit bigger, because it always ruined the sponge. But there are some holes you can do that with and some you can't, because some are bigger and some are smaller. And the sponge always works, but there's all this empty space in it. And that's what the ice in space actually is like. And that means it's a very unusual material. It has really good chemical catalytic properties. So we have interesting chemistry that happens because there's a large surface area, and also because these pores are important. In industry, people use something called zeolites a lot. It's a material which has lots of pores in it to do lots of interesting catalysis and cleaning up processes, because you can trap gases and horrible materials inside these things. Well, this amorphous ice we have in space does exactly the same thing. Right. It can trap things in it and do interesting chemistry. So these little icy particles which are colliding together to build planets are also doing all the chemical processing that we find interesting to build the complex chemistry. And so when we want to study that, we use slightly different instruments which can sort of recreate the low temperatures and pressures we find in space. And then we can look at how the ices behave, and we can do that here in the lab too. So some people do that side of things. Right. And then on another side of my group, we actually want to understand what the properties of this material are. And that we can't show you here because we have to go to the neutron scattering source down at Rutherford Appleton Labs. It's a big national facility. And we use neutrons, and the neutrons basically come in, and when they interact with the nuclei of the material, so what's in the centre of the atom rather than the electrons, what they do is they scatter in different directions, and depending on the distance they fly between one nucleus and the next, we get different patterns, and we can start to understand the structure. And in the UK, we have one of the world first instruments that can study this on a molecular scale, but also on a much bigger scale, bigger being nanoscale, so really tiny actually, but big enough that we can see these pores and this porosity in the material. And so we study quite intensely from a very sort of fundamental condensed matter physics perspective what the behaviour of this material is doing. And we do that in collaboration with some condensed matter physicists who come from Austria.
Very nice. Where there's plenty of snow and ice.
Where there's plenty of snow and ice, but not this kind of snow and ice. We don't find it on Earth. And we're able to sort of complement those kinds of studies by doing computer simulations of the material as well. They're called molecular dynamics simulations. On a very basic level, they take Newton's equations of motion, so something maybe most people met at school about how forces are linked to mass and acceleration, how velocity is linked together. And we solve those for every atom in our system. And it can start to tell us something about how the material behaves and how the material grows and how it collapses again. And so we put all of that knowledge together to understand the material. We then understand the chemistry, and we then understand how those materials and chemistry collide together in the planet formation process.
That's astrochemistry.
That's
in a nutshell.
astrochemistry in a nutshell. And then the very last thing we do is we have to actually put this back in a context. So we put it in a context where the chemists understand or the physicists understand. Then we have to jump back one more time and put it in the context the astronomers understand, because really they're our end user, they're our consumer, if you like. And so we have to make observations with telescopes. And again, we don't unfortunately do that here at the Open University. We generally use infrared telescopes to observe ice. So that might mean satellites in space, or it might mean large telescopes, mostly now in the southern hemisphere. And we have students in my group who also study the ice and look at the spectroscopy, how the ice and light interact, to try and understand, or it's like puzzle solving actually. You can't go there and get a bit of space ice and bring it back and have a look at it. So you have to interrogate with your telescope what it looks like and what's in there, and use that to inform your experiments, and use your experiments to inform your analysis of your observations. So we go in a very big circle. It's a very interdisciplinary field. That's what I love about it, that we jump in many different directions and talk at the end to the astronomers. And yeah, that's what astrochemistry is.
Great. So when's the next parabolic flight and the next set of experiments?
Oh, well, we have one student who's working currently on the parabolic flight, putting it all back together again after the last time. But we just heard we've got a new grant. So in September, there will be a new member of the group joining us for 3 years. And so we're really hoping that our next parabolic flight will be in 2015 or early 2016. It's a pretty exciting time for us in the UK because until a few years ago, when I first started this work, really, I started it actually when I was still a postdoc and not in the UK. And when I first moved back to the UK, it was necessary always to collaborate with our European colleagues because we didn't have access to those facilities. And just 2 years ago, the government signed up to ELIPS, which is the ESA programme, the European Space Agency programme, which allows us access to parabolic flights and drop tower experiments and so on. And you may be aware that in 2015, in November 2015, Major Tim Peake will fly to the ISS, and he will be our first European-trained British astronaut. So the first one that's really come through ESA and through the selection process. I'm very jealous. I got to the last 400, but they didn't pick me. But never mind, Tim's going, and he is a wonderful ambassador for us, a really lovely, lovely person. And actually, the kind of experiments we do here in parabolic flight are really a precursor to what we also want to do on the space station. And nobody gets to fly experiments, complicated experiments on the space station until they've really proven their worth in parabolic flight. And you can't just go and fly on a parabolic flight. You have to have a good reason for using it, and like we do, the very low velocities. And that means if we want to go to even lower velocities with these particles, we actually have to have long duration microgravity. We need the ISS, which is almost constantly in microgravity. Actually, the worst thing about the ISS is if an astronaut goes to the toilet or something, it actually ruins the microgravity for an experiment. So while you're experimenting, you're hoping they're not all moving around in the space station. It can already affect the gravitational field. Unfortunately, this time when Tim flies in 2015, our experiment that will eventually do that, which is called ICAPS, Interactions of Cosmic and Atmospheric Particle Systems, is still in the final stages of being built by the European Space Agency. It will now fly in 2017. So maybe if we get Tim another flight in the next few years, then he might actually be doing these experiments on board the space station on our behalf and sending us the data back in a few years' time, which is pretty exciting for us.
Best of luck with that.
Thank you.